Hey YouTube, and welcome to my channel MSP Maxwell. Or maybe once I become more creative I'll think of a better name. You can probably guess, my name is Maxwell, and this channel is my way of sharing my journey as I learn about different STEM concepts in math, science, and programming. So in this series, Animating Physics with Python, I learn about some physics concept and then try to code an animation to demonstrate it using the popular programming language Python. After which I share how I coded it with those of you on YouTube who are interested. Today, the first physics concept we're going to look at is projectile motions. Projectile motion, which is just looking at the path of a projectile after it's been thrown in the air. But before we code, I want to do a bit of a review on projectile motion for those who may want to follow a bit better when I do go out and code it. It's not going to be a super comprehensive guide. It's mostly just showing the equations that we're going to use once we get to coding. So first, we got to go over some terms. Displacement, which we denote with an S, is how far an object is from a given starting point. And we call it's different from distance in this way. So basically, if your starting point is here, and say you have some object that's moved this way, 5 meters, its displacement will be 5 meters. It's 5 meters away from the starting point. If you were to go back 2 meters, its displacement now would be where you are now from the starting point. So if we draw a dotted line, this is 3 meters. And so your displacement would be 3 meters. If we were using distance, or at least in physics, distance would be like total distance traveled. So in this case, distance would actually be 7, because total distance traveled would be 5 forward, 2 back, 5 plus 2 is 7, and so your distance would be 7. But we only care about your distance from a starting point, and that's why we use displacement. And the unit obviously is just a distance unit, so meters, kilometers, stuff like that. But we'll be using meters mostly. Next one is velocity, which is how fast a projectile is moving, and it's given by meters per second or kilometers an hour. It's pretty obvious. We use cars every day, and cars show us how fast they're going kilometers an hour. And we have acceleration, which is the change in velocity after a given time. So, for example, if a car is driving at 10 kilometers an hour, and it's accelerating at 5 kilometers an hour squared, which is the unit for acceleration, you would know that after 1 hour it'd be going 15 kilometers a second, and after another hour it'd go 20, then you have 25, and so on and so forth. And so so the acceleration is just the difference, how fast velocity changes per time period. So here, this would be 5 kilometers. This would be an increase of 5 kilometers. 5 kilometers like an hour each hour. This is why we call it kilometers an hour squared. It's like 5 kilometers per hour per hour. But in this example, we'll be using meters per second squared. And last thing we're going to review is Newton's first law of motion, which just states that an object at rest or in motion will remain at rest or in motion so long as an external force does not act on it. So let's say you have some object and it's moving this way. As long as there are no other forces coming at it, so long as these don't exist, it'll keep moving in that direction indefinitely. You don't really see that in real life because if you roll a ball, there's friction with the ground. Let's say there was no friction, no air resistance, no nothing. There's just no forces acting on the ball. That ball would go on forever. Nothing would stop it. And that's something that will affect what equations we have to use and when. Alright, so we're going to move on to the first thing to understand, which is when you look at the motion of a projectile moving in a curved path, like this, moving in this curved path, we can look at its vertical motion and its vertical motion separately. So, I mean, let's explore what that actually means and what that looks like. So, say you have a soccer ball. See, this is our soccer ball, and it's been kicked at an angle of 75 degrees at a velocity of 20 meters a second. So, or an angle of 75 degrees is like a rough 75 degrees. Hi, this is future Maxwell butting in. Old Maxwell repeatedly made the mistake of calling vertical horizontal and horizontal vertical. So in an effort not to look stupid, we're going to fix that here. And so, again, we can treat our velocity like the hypotenuse of a right triangle, of which its length is 20, and this angle being 75 degrees. And so when we complete this right triangle, sorry for the beat, when we complete this right triangle, we get these two sides. And imagine this extends all the way. And this horizontal side will actually be representative of our horizontal velocity, and this vertical side will be representative of our vertical velocity. And the two combined make our actual velocity. And so here, to get our horizontal velocity, it's just some simple trig, and in this case it would be our big V, our actual velocity in both directions, which would be 20, but here we'll call it just a big V, cosine times cosine theta, theta being the angle here. And so for our specific example, it would be 20 times cosine of 75. And for this side, I don't know how Khan Academy draws so nicely. But for this side, and our vertical side is our vertical velocity, and it would be v times the sine of theta. And so for this specific example, it would be 20 times sine of 75. And so to recap, this is our horizontal velocity, and this is our vertical velocity. Well, this would be our velocity combined in both directions. And back to the actual video. And we'll calculate those real quick. We'll call this vertical velocity V and horizontal H. And so we can grab a calculator real quick and figure out what these should be. So for the vertical velocity, it would be 20 times not 75. Gotta put this first, sine of 75, which equals 19.3. We'll just use one decimal place. 19.3. I forgot to add a unit. Let's say it's going meters a second. And the horizontal velocity would be 20 times first, the cosine of 75. Wow, it's going really slow. I might know that. Yeah, that equals, yeah. 5.1. Actually, we'll go significant figures. So 5.18 meters a second. And this, like these values should, kind of make some intuitive sense, because if you throw something at a high angle, you wouldn't expect it to move too far horizontally. Like here, it's going pretty slow horizontally, but it's going to go pretty fast vertically. So it's going to move far vertically. And say we picked a lower angle, it'd probably go slower vertically and faster horizontally. And so these values check out. Now that we can figure out how fast a projectile is moving in a given direction using just basic trig, we need to be able to know where this projectile is at any given point in time. And so for the horizontal direction, we're looking at a pretty simple case. It's pretty simple to know where this soccer ball will be horizontally, because we're going to assume there is no air resistance, and basically no forces in the horizontal direction. Which means, according to Newton's laws, our velocity should not change whatsoever. There should be no acceleration, which allows us to use a pretty simple equation to figure out where this ball is at any point in time. And so the equation we can use is this. Basically, our final displacement, which we'll call SF, will equal our initial displacement, SI, plus our velocity times time. And this is pretty much what you would do in your head. It's a pretty intuitive equation. It's what you would do in your head if I asked you, like, how far would you go if you were traveling 5 meters a second after 3 seconds? You do 5 times 3 quickly in your head. You get 15, and you get, okay, I'll be 15 meters away after 3 seconds. And this initial displacement is just adding in the fact that you may be already some distance away from your starting point. So say you were already 3 meters away, and you add that 15, you get 18. And that would be your final displacement. For us, we're going to assume that our initial displacement is just 0, so really we could get rid of this initial displacement and just have velocity times time, which is a pretty intuitive equation. And we can let's put this into decimals so we can look at our specific example a bit. And the thing we can do is we can make this a function of time, so we can look at the values at every point in time. Now our velocity, our horizontal velocity, was 5.18. Yep. 5, not 6, 5.18 times time. And you get this straight line. It's a linear equation. And it's pretty simple. So at 0 time, 0 seconds, we've not moved. At it moves pretty fast. Let's zoom in. Yeah. So after 1 second, which is all the way up here, we've moved already 5 meters. After another second, this is time equals 2, we move 10 meters, so on and so forth. And so now we can, so now we know the horizontal position of this ball at any point in time. But the thing is that this equation kind of assumes that we keep going on forever. So we need to figure out at which point our ball hits the ground so we know when to stop. Because for our case, we'll just assume that the ball stops moving after it hits the floor once, just for simplicity's sake. So if the ball hits the ground after 2 seconds, we only care about our final displacement for about 2 seconds, and so on and so forth. But to get that, we need to realize that okay, we hit the ground when our vertical displacement is 0. So we have to look at our vertical displacement. We need to find a function that will describe our vertical displacement over time. And so vertical displacement is not as simple. We cannot use this same equation because this same equation assumes that our velocity remains the same. For the horizontal direction, that was fine. It does remain the same. But for the vertical, it does not. Gravity actually accelerates everything on Earth downwards at 9.8 meters per second squared, which means as our ball goes up, our vertical velocity decelerates, and as it comes down, it accelerates. And thankfully, there is an equation that factors in acceleration, and it is this. It's a bit more unintuitive, but we're just here to get the equations and pull out our code, so it shouldn't matter too much. Our final displacement will be equal to our initial displacement plus velocity times time. Oh, looks like the same, except we add another factor, which is a half acceleration, half times acceleration times time squared. This is what we're going to use for our vertical velocity. So the beginning is like the other one, but then you have this other term, which is just a half times the acceleration we're experiencing times time squared. And for our example, we're going to assume we're starting on the ground, so our initial displacement is just 0. And so really it's just velocity times time plus a half at squared. And for A will be, in our case, the only acceleration happening is due to gravity, and our acceleration due to gravity will be negative 9.8. And it's negative because it's moving downwards, but this is what we'll plug in for A, negative 9.8 meters per second squared. Well, forget the units, we don't need the units. And so after adding A, so, well, if you substitute A in, we'll keep V unsubstituted, even though we know what it is. It will look like this. V times T minus, not plus, minus a half times 9.8 times T squared. And this will give us our vertical displacement at all points in time. And so let's plug that into decimals and see what that looks like. We'll call this S of T again, and we get we gotta use our vertical velocity this time, 19.3 times time minus a half times 9.8 T squared. Oops, that's an at sign, squared. And wow, this graph kind of looks like the path our ball would take, but it's not. It's just how far up or down, or just how far up or down we are vertically. So don't confuse this as like the actual path. It's just how far up we are or how far down we are. And so with this equation, we learn a lot. You learn a lot here. So we've got at 0, 0, obviously, we've got it's on the floor, and so it would not be moved at all. But as we go up, I'll get like seconds. Let's look at 2 seconds. 2 seconds is actually very close to our apex. So let's see, at 2 seconds, we are, I guess our apex is actually at 1.9 seconds, and we are 19 meters up in the air. So after basically 2 seconds, we'll be 19 meters up in the air. After 2.8 seconds, we'll have gone down a bit. We'll be at 14 meters up in the air. And finally, at a little under 4 seconds, we'll finally hit the floor again. And that's where we'll stop our animation. And so, with these two equations, we can know where our ball is at any point in time. I can just pick a random second, like 1 second is about here, 5 meters up in the air. So it's 5 meters up in the air, and then I look at our, that's for no, I picked the wrong graph. That is for our horizontal. So after 1 second, we are again 5 meters right, and how far up are we? Usually this blue graph will be 14 meters up. And so with that two points of information, we know where our ball is at. And that's really all we need. And also with our vertical, with our graph for the vertical displacement, we know it will be about 4 seconds when we hit the floor. And so we know where to really stop for our horizontal. So for our horizontal graph, at about 4 seconds, we know we'll hit the floor once we're about 20 meters away. And so that's how we're going to know when we hit the floor. But actually, in code, it's not going to be that simple. So there is last one thing we need to know in advance, and it's how long it will take for us to hit the ground. With decimals, you can just plug this in and see, okay, boom, 3.9 seconds and we're on the floor. But when we're actually coding this, we're not going to be able to know that until we reach that point, and it's not going to be that simple. So we're going to need to know in advance how long this trip is going to take. And so that's not too hard. We just take our equation that we use for our vertical velocity, which is this. This is the one we use for our vertical displacement, And we use some algebra to solve for t. And we set our final displacement to 0, and we use our algebra to solve for t. And so we'll move a bit. Let us pull out algebraic hats. We get 0 equals velocity times time plus a half acceleration. Now we'll plug in gravity. Yeah, we'll use the gravitation. We'll use the one for gravity. So minus a half 9.8 times t squared. We can factor out t, get v minus a half times 9.8 t. And because we have a 0 on the left side, we know that either t or this thing in parentheses has to equal 0 to satisfy this equation. So we have two solutions. And obviously, one of these equations will be 0 equals t. And obviously, when t equals 0, we know that our vertical displacement is 0. So we don't care about this solution. We actually care about this solution, which is 0 equals v minus a half 9.8 t. This is the second solution for when our vertical displacement is 0, and it's the one we care about. And so we'll solve for time, move down a little bit, and we get negative v equals negative a half 9.8 times 9.8 t, which I just subtracted v from both sides, and now we're going to divide by negative a half times 9.8 on both sides, which leaves us with negative v divided by negative a half times 9.8 equals t. And really, we don't need these negative signs because two negatives in a division statement just make a positive. And now we have this equation. T equals our velocity, or divided by a half times 9.8. And that will give us our solution. So we can just check that real quick and see if it matches up with a little under 4 seconds. So we said that our velocity was 19 point something. So let's check that again. Vertical velocity was 19.3. So 19.3. I'll put our equation for time again so you can see what I'm doing. We got 19.3 divided by 1/2, which is just 0.5, times, actually I want to put this in parentheses to make sure the calculator follows the right order. So 0.5 times 9.8. You get 4.9, which is not what we expected. What's up with that? 4 point. Oh, I keep forgetting to hit the equal sign. I don't know why. But 3.93, which basically is our second solution, matches up perfectly. 3.93 here. Decimals rounded up after those significant figures. And so there it is. And so we can use, when we get to our code, we can use this equation to figure out how long we're going to be in the air for and work with that. So that should be all the math we need to know. And so next video will be me starting the code and seeing these equations in action. So it's always fun to realize that math actually works. Right? See you next video.